Alright, hi guys. This is our second area between two curves video, and this one is going to be about finding area with a little bit more challenging situations. So the first example here says find the area of the region bounded by y equals 1 minus x squared and y equals 1 minus x. So what I'm going to do is go through my steps, and step one is sketch a picture. So step number one, sketch a graph. And so if I'm going to sketch this thing, hopefully I can kind of do it by hand. I think I can. I don't think I'll need a calculator. So y equals 1 minus x squared, I know is a parabola. Up 1 and flipped upside down. It's something that looks probably like this. It's up here at 1 and it's pointing downwards. And I better label this y equals 1 minus x squared. And then the other curve is y equals 1 minus x. That's a straight line, has a y-intercept at 1, and it's going negative slope, down 1 over 1. In fact, it's going to hit the curve right here at 1. So we're going to have this straight line pointing down, something like this. And we'll work our way back. There we go. And I'm going to write this is y equals 1 minus x. So our big job was to find the area bounded between these two graphs. So trapped in the middle here. Find this area. So I'm going to shade it in. So we have a perfect setup. We drew the graph, we labeled, we're ready to move on to step number 2. And step number 2 is going to be our setup. We're going to do our integral setup. Sorry, my cell phone. Okay, step number 2, integrals, integral setup. Shoot. Okay, so what we're going to do is before we even make the integral, we're going to draw a rectangle inside of here, because the idea is we're adding up infinitely small little rectangles. So I'm going to use a different color so I can actually see. I'm going to make a little like black colored rectangle right in here. There we go. And then I'm going to copy that little rectangle strip over here, and we're going to label it with a width and a length. We know the width of our rectangle is always infinitely small because we're going to cram billions of these little rectangles in here. So the width always is delta x. We know the length of the rectangle is always the top minus the bottom. So the top of this rectangle hits the parabola. So the top is 1 minus x squared. And then I'm going to subtract the bottom of this thing. The bottom of the rectangle hits right on this line at 1 minus x. And so there's my setup for my length. I'm going to go make my integral next. Before I do, it might be helpful to myself to clean this up. So what I'm going to do is rewrite this. Length really equals 1 minus x squared, and then take this subtraction sign, distribute it in, minus 1 plus x, which means the minus 1 plus 1, we're going to cancel those. Length equals negative x squared plus x. So my integral for area is going to look like this. Area equals integral length, negative x squared plus x, we just solved for that, times width, delta x. And there's my setup. The only other thing I need to figure out are bounds. And a lot of times the problems give you the bounds. In this problem, they did not give you the bounds. In fact, you can see where they're at because we did a good job graphing. But let's say you kind of hesitated, or you used your calculator, you just didn't know how to find the bounds very well. This is how you go about it. The bounds are wherever the graphs cross each other. So where does the parabola and the line meet? Well, where does the 1 minus x squared parabola equal the 1 minus x line? So anytime you need to find the bounds yourself, set the two curves equal to each other, and that'll be how you find your point of intersection. I'm going to add all this stuff over. Like I'm going to take this and move them over. So 0 equals 1 minus x plus the x squared and then minus the 1. And I'm going to get 0 equals negative x plus x squared. The 1's will cancel. And to solve this, I'm going to factor out an x. So 0 equals x times negative 1 plus x. And if I'm factoring this, I know I get x equals 0 and x equals 1 as my two answers, which makes sense because that's what happened on our graph. Our points of intersection are here at 0 and here at 1. So these are also going to be my bounds from 0 to 1. So on my integral over here, I can write 0 to 1. So now we go on, after we found the bounds, we go on to step number 3, which is going to be just solving this thing and getting an answer. If you want to pause the video and try it yourself and see if you got this down, go for it. Basically what you're going to do is reverse power rule all this stuff. So negative x squared is negative x cubed over 3 plus x becomes x squared over 2 bracketed from 0 to 1. So plug in top minus the bottom. We're going to have, plug in the 1, we're going to have negative 1 cubed over 3 plus 1 squared over 2. There's the top. Minus plug in 0, we're going to have negative 0 cubed over 3 plus 0 squared over 2. So we can tell all the 0 stuff is going to cancel. We're really looking at basically, what do we got here? Negative 1/3 plus a half. So we're going to get negative 1/3 plus a half, which with common denominators, we make these into sixes. So this is really negative 2 sixes plus 3 sixes, which equals 1/6. So the area of this small little shaded region is 1/6 units squared. And that's my answer. So sometimes you have to do a little bit of work to figure out the bounds. You have to set the curves equal. Beyond that, it's still kind of the same type of problem. When it gets really complex is when you have multiple intersections. So let me show you another example. Imagine I had given you a problem like this. Imagine I had said something like, find the area bounded between y equals x and y equals x cubed. Well, we know how to graph both those functions. We know x cubed is the one that kind of goes like this. So here's y equals x cubed. We know y equals x is a straight line that goes through the origin, so probably something like this. I'll extend it out here. Y equals x. The area that gets bounded between these graphs happens actually twice. It gets bounded in between here, and then again up here. So when I ask you to find the area, you've got a new dilemma. You've got to draw your rectangle strips in two locations. One strip goes here, and one strip goes here. And you're going to notice right away that the top and bottom of these strips change. Like in this first area region, the top of the rectangle is on the curve. But on the second region, the top of the rectangle is on the line. So to solve for the area, this is going to actually require you to set up two different integrals. So we got step 1 totally accomplished here. Looks like we've drawn the graph. We're actually on to step 2 already. I'm just not labeling now. So step number 2, we're going to do the integral setup. We're going to actually split this up into two integrals. Before we do, I want to know where are all the points of intersection for my bounds. So I'm going to write bounds over here. And I'm going to set these two curves equal to each other. I'm going to set the x cubed equal to the x. And I'm going to solve for where they cross. So subtract the x over. X cubed minus x equals 0. Factor out an x. So I have x times x squared minus 1 equals 0. Then factor x squared minus 1 into two parentheses. That'd be x plus 1 and x minus 1 with an x in front equals 0. Which means I have three answers here. I have x equals 0, x equals negative 1, x equals positive 1. And these are going to make up my bounds. That means this thing right here crosses at negative 1. 0, I could tell. I saw it hit the origin right here. And then positive 1 must correlate to this point up here, positive 1. So you know how we drew our rectangles and we have our little strips? We have two area regions. So I'll call this region A, the first region, and I'll call this region B. For region A, here's what my rectangle is going to look like. Region A has this little rectangle with a width and a length. So width and length. The width equals an infinitely small width. We're cramming millions of these in here, infinitely many rectangles, so delta x. The length is the top minus the bottom. So in region A, the top curve is the x cubed, and the bottom curve is the straight line. It's the x. So we get x cubed minus x. That's region A. For region B, which is now going to turn into a red shaded region so I can differentiate the two, I'm going to write region B down here. The little rectangle that fits inside that space, well, the width is still delta x, but the length is going to change. The top of this rectangle hits the line, so the top is x. The bottom of the rectangle hits the curve, x cubed. So you can see how the top and bottom switched on these two different parts, region A and region B. So when we go to set up our integral, I don't really need the picture anymore. I'm going to have two integrals. I'm going to have the first integral with x cubed minus x times delta x. And I'm going to have the second integral with x minus x cubed delta x. And we're going to add their answers together. So I'm going to add these answers together for a total area. The bounds, I guess I probably should look at my graph. The bounds on the first region, region A, the bounds go from negative 1 up to 0. So I'm going to write negative 1 to 0. And the bounds for the second region go from, if you look at your graph, from 0 to 1. So now you're just saying this entire thing equals the area. Now solve both integrals and combine your answers together and you'll be ready to go. So I'm going to write equals, and we'll give both of our answers here. X cubed is going to be x to the 4th over 4 minus x becomes x squared over 2, bracketed from negative 1 to 0. Then we'll add this on to this one, which is going to be x becomes x squared over 2 minus x cubed becomes x to the 4th over 4, bracketed from 0 to 1. And let's just carefully plug everything in. If I plug in the top bound for this first one, plug in 0, I'm going to have 0 to the 4th over 4 minus 0 squared over 2 minus, plug in the bottom bound, negative 1. It's going to be negative 1 to the 4th over 4 minus negative 1 squared over 2. So that is the first part of this problem. And then whatever that gets you, we're going to add that to plug in this thing. It's going to be plug in 1 squared over 2 minus 1 to the 4th over 4 minus plug in 0 squared over 2 minus 0 to the 4th over 4. And again, it's coming down to some fractions here. So now you just got to carefully clean this thing up. I can't remember what the answer is, so we're going to work it out real quick here. All the zeros cancel each other out. So these cancel and these cancel. So that's kind of nice. Negative 1 to the 4th becomes positive 1/4. Negative 1 squared becomes positive 1/2. But there's a subtraction sign, so we have minus 1/2. So 1/4 minus 1/2. And then remember there was a negative out in front. So we get this. Plus, on this side we have 1 squared over 2, so 1/2. Minus 1 to the 4th over 4, so 1/4. So really, if I was to distribute this negative sign in, I would have negative a fourth, negative a half becomes plus a half, plus another half, plus a negative a fourth. So this is what I'm working with. So a half plus a half, a negative fourth plus a negative fourth. So I'll put the fourths together. Negative fourth plus a negative fourth is negative 2/4 plus a half plus a half. And negative 2/4, oh sorry, you can't even see what I'm doing. I put the fourths together, got negative 2/4. That reduces down to negative a half plus a half plus a half. And negative a half plus a half cancel. And so my answer is 1/2. The area of these two regions combined must be a half. And the answer is going to be units squared. And there we go. So that was just a whole bunch of fraction work at the end. But big thing is if you end up getting two regions, so something that looks like this, you have to split it up and make two integrals. And that's where it gets real tricky. So look to the next video and we're going to talk about what happens when we start shifting.